Private Outlaw sat in a lightless, frozen foxhole. The year was 1944, and the silence of the European winter was absolute until the horizon suddenly tore open. There was a rhythmic, mechanical thumping in the distance, a sound that did not belong to nature. Outlaw gripped the cold steel of his rifle and counted the seconds between the flashes on the horizon. He could not see the batteries, and he could not see the men pulling the lanyards miles away. He only knew that the ground beneath his boots was beginning to vibrate. This was the moment where the industrial power of the 20th century made itself known to a single human being. It leads us to a question that defined the entire era of mechanized warfare. How did the gun survive when the world outran it? To understand why Private Outlaw was trembling in that hole, we have to go back nearly a century. In those days, the gun was still a stubborn iron beast. Before the 1890s, artillery was essentially a massive shotgun on wheels. When the weapon was fired, the laws of physics took over. The entire carriage would violently leap backward several feet from the force of the explosion. The crew then had to manhandle several tons of iron back into position and re-aim from scratch. It was a slow, exhausting process that made precision a secondary concern to sheer volume. If you were an artilleryman in 1870, your job was more about muscle than mathematics. Then came 1897. The French introduced the 75mm field gun, and it changed the nature of combat forever. This was the first quick-firing gun. It utilized a hydropneumatic recoil system, a series of pistons and oil-filled cylinders that absorbed the energy of the shot. The barrel hissed backward, but the carriage stayed perfectly still. Gunner DuPont was one of the men who lived through this revolution. He wiped a smudge of grease from the recoil slide and marveled that the carriage didn't budge an inch after the shot. For the first time, a gunner did not have to get off his seat. He could keep his eye on the sight while the loader slammed another shell into the breech the moment the barrel returned to battery. A single crew could now fire 20 rounds in a minute. During its first demonstrations, it rendered every other artillery piece on the planet obsolete overnight. But innovation is one thing. Organization is another. As the First World War ground on, it became clear that the god of war was a logistical nightmare. Allied armies were using a chaotic mix of different calibers and parts that could not be shared between units. This is where Colonel Westervelt enters the story. Westervelt was the architect of standardization. He sat in rooms filled with blueprints, arguing for a global artillery language. He led a board that looked at the wreckage of the Western Front and realized the gun had to be modular to survive. Westervelt pushed for the standardization of the 105 and 155mm calibers. He saw that the future of the weapon was not just in its barrel, but in its ability to be integrated into a fast-moving supply chain. By 1939, the gun had found its voice, but the enemy was starting to move faster than the gunners could turn their wheels. This brought about the challenge of the moving target. The moving target was the conceptual enemy of the 20th century, the reality that armor was getting thicker and engines were getting faster. Artillery was no longer firing at a static fortress. It was trying to hit a tank moving at 30 miles an hour across broken terrain. This forced an evolution in how armies moved. The transition from horse-drawn pieces to motorized carriages was driven by the necessity of keeping pace with armored formations. Yet there was a profound gap between this industrial potential and the reality of the front line. While engineers were designing self-propelled guns, major powers remained heavily dependent on horses well into 1945. This defined the era, a collision of the Napoleonic past and the atomic future. On one side of the battlefield, the proximity fuse turned anti-aircraft shells into lethal autonomous hunters. On the other side, crews faced the back-breaking labor of breaking down a mountain gun into 8 mule loads in the freezing rain. At the Battle of Albert, gun crews huddled in camouflaged pits as the earth shook around them. Their faces were smeared with mud as they timed their loading rhythm to the heartbeat of the firing sequence. They were operating in a world where a wet finger in the wind was still the primary way to calculate a trajectory. They were fighting against nature as much as they were fighting against the enemy. This was the grinding fatigue of the Aleutian Stair, where men operated equipment that barely changed for decades. The evolution of the gun was a frantic scramble to keep the weapons firing when technology went obsolete, almost as soon as it left the factory. It was a transition from the glorified fireworks of early rockets to the independent, multi-warhead missiles of the late 20th century. This history spans the contrast between the dirt-filled reality of a trench and the sophisticated technology of the space age. The artillery had to evolve, or it would be left behind in the mud. To understand the moment the modern world began for the artilleryman, you have to look past the smoke and focus on the wheels. Before the turn of the century, firing a cannon was a violent, primitive wrestling match. When the powder ignited, the carriage would leap backward and claw into the earth. The crew had to drop their tools and grab heavy iron handspikes to manhandle the weapon back into its marks. It was a cycle of exhaustion that limited even the best crews to perhaps 3 aimed shots every minute. Then came the quiet demonstration in 1897 that would soon haunt every general in Europe. The French unveiled their 75mm gun, and to the observers, it looked like magic. The gun fired, and while the barrel hissed backward in a blur of motion, the wheels and the trail stayed perfectly still. Gunner DuPont spent his days maintaining the complex arrangement of pistons and oil-filled cylinders that lived under the barrel. He would wipe a smudge of grease from the slide, noting how the metal remained cool even after a rapid-fire drill. For DuPont and his crew, the revolution meant they no longer had to stand clear of the wheels to avoid being crushed by the recoil. They could stay on the gun. The loader could have the next shell ready before the previous casing had even hit the mud. A single battery of these guns could now do the work of an entire regiment of older pieces. The French 75 could cycle through 20 rounds in 60 seconds. It wasn't just a faster gun, it was a different category of existence. The god of war had transitioned from a slow hammer into a precision machine. As the first global conflict expanded into an industrial catastrophe, technical brilliance hit a wall of human chaos. By 1918, the Allied armies were struggling with a mess of mismatched equipment. A British battery might be firing shells that were a fraction of an inch different from the American battery positioned half a mile away. If a supply column took a wrong turn, an entire division of guns became useless piles of iron because the ammunition was not interchangeable. The logistics were failing the technology. This is where Colonel Westervelt enters the story. He was not a man of the trenches, but a man of the blueprint and the ledger. He headed a board of officers tasked with making sure the next war did not collapse under its own weight. Westervelt sat in rooms filled with technical drawings, arguing with engineers and bureaucrats about millimeters and kilograms. He saw that the future of the gun was not just in how fast it fired, but in how easily it could be fed. He saw the weapon as a supply problem. Westervelt pushed for a concept that seems obvious now, but was revolutionary at the time. He argued that the world needed a global language of artillery and fought to narrow the field of calibers down to 2 primary pillars. These were the 105mm for light, mobile support, and the 155mm for heavy long-range destruction. Those 2 numbers, chosen in an era of horses, are still the primary calibers used by almost every professional army on Earth today. Those 2 numbers still define modern war. He realized that the gun had to become a modular component of an industrial machine. The weapon had to use the same shells, the same fuses, and the same repair parts, regardless of who manufactured the carriage. He was building a system designed to survive the challenge of a faster, more armored enemy. He knew that if the gun could not be moved by a truck and fed by a factory, it would be left behind. The gun had to move or die. By 1939, the god of war had found its voice, but the enemy was starting to move faster than the gunners could turn their wheels. The era of the static horse-drawn siege was ending, and the race to keep the gun mobile had begun. The era of the horse was over. Consider the predicament of a gunner in 1940. For 40 years, the artillery had been perfecting the art of hitting a fixed point on a map. But by the middle of the century, the moving target had evolved into a steel reality that could cross 200 yards of broken ground in less than 30 seconds. This was the moment the gun had to stop being a siege tool and start being a predator. The gun had to become a predator. To understand why this shift happened, you have to look at the pivot of the 8.8mm anti-aircraft gun. Originally, this weapon was never intended to fire at anything on the ground. It was a defensive shield designed to throw a 20-pound shell 5 miles into the sky. But in the heat of the North African desert and the plains of France, the tactical reality shifted. The tactical reality had shifted. Gunner Schmidt was one of the men who participated in this transformation. In the desert, he found himself staring at a shimmering horizon, where a column of British armor was kicking up a wall of dust. To survive, Schmidt had to perform a maneuver that went against every manual he had been trained on. He grabbed the heavy iron handwheels and began the grueling process of cranking the massive barrel downward until it was parallel with the sand. The 8.8 was a high-velocity masterpiece. capable of firing a shell at 820 meters per second. When Schmidt leveled that barrel, he was turning a defensive skyscraper into an offensive scalpel. At a range of 2 kilometers, the shell hit with such violence that it could punch through the thickest armor of the era and exit the other side. The shell punched through both sides. While Schmidt was refining the art of the precision shot, a different evolution was happening on the Eastern Front. If the 88 was a scalpel, the new Soviet rocket technology was a sledgehammer. By 1941, the Red Army realized they could not out-engineer German optics, so they decided to overwhelm the target with sheer volume. They chose volume over precision. Loader Ivanov stood in the knee-deep Ukrainian mud, his hands slick with freezing rain as he worked. His job was fundamentally different from the artillerymen of the past who dealt with complex breach systems. Instead, he was sliding long rockets onto open steel rails mounted on the back of a standard truck. There was no precision in the loading, only a desperate race against the clock. Ivanov worked in a race against time. To understand the impact of what Ivanov was doing, you have to look at the way the rockets left the rails. A single truck could unleash 16 projectiles in less than 10 seconds. This was the birth of area denial, turning a square kilometer of earth into a landscape of fire and shrapnel. For the men on the receiving end, the sound was a terrifying low-frequency howl that gave them no time to react. The rockets left a trail of fire. Ivanov and his crew lived by a new doctrine of firing and vanishing. Because the rockets left a massive signature of smoke and dust, they were a beacon for enemy counter-battery fire. The moment the last rail was empty, the driver would slam the truck into gear and disappear into the forest before the first German shell could find them. The driver vanished into the trees. By the middle of the 1940s, these two extremes had pushed the traditional field gun into a corner. The artillery was caught in a leapfrog of steel, where the gun had to get bigger as the armor got thicker. By the time the dust settled in 1945, the weapons had reached a physical limit. The artillery reached its physical limit. The barrels were longer, the shells were heavier, and the carriages were becoming massive. They required specialized prime movers just to cross a bridge or navigate a muddy road. The gun had grown into a monster that was beginning to consume the very logistics meant to support it. The weapons were consuming their own support. As the war ended, the gun had grown too heavy to survive the coming age of the atom. The world was moving toward a new kind of speed that could not be solved by cranking a handwheel faster. The moving target was about to become a global threat, and the gun would have to find a way to stay relevant. The tanks remained while the planes vanished. To understand where the gun went after the fires of 1945 died down, you have to leave the mud and the cordite behind and descend into the earth. By the 1960s, the ultimate evolution of artillery had become a subterranean existence. The frantic, sweating loading crews of the world wars were replaced by a profound mechanical silence. In these hardened bunkers, there were no horses, no tractors, and no horizons. There was only the low hum of cooling fans and the steady amber glow of vacuum tubes. Silo Chief Petrov was a man who lived at the center of this new reality. He sat in a concrete room buried deep beneath the steppe, his world reduced to a series of dials and a single physical launch key. For Petrov, the gun had become a missile, and the artilleryman had become a custodian of the end of the world. He did not look through a panoramic sight at a distant ridge. He watched a single red light on a console. In the old wars, a soldier knew he was in the fight because the ground shook and the air smelled of burnt powder. In the silo, the only sign that a war had started would be a light changing color. It was a war of readiness, not of action. This shift was driven by the realization that the moving target had become a global threat. In 1962, during the Cuban Missile Crisis, the weapon at the center of the tension was a direct, liquid-fueled descendant of the rockets that had fallen on London decades earlier. But these were not field guns you could wheel into a tree line. They were massive, temperamental towers of steel that required hours of fueling and a small army of technicians just to prepare for launch. The gun had become a symbol of brinkmanship. It was no longer about the act of firing, but about the fear that the weapon might fail before it ever left the ground. If the enemy knew your missiles were vulnerable while you were fueling them on the surface, the weapon was useless. Engineers realized that if the gun was going to survive in the atomic age, it had to be hidden, or it had to be instant. The weapon had to become immediate. This led to the development of cold launch technology, a breakthrough that changed the physics of the silo. In a traditional launch, the engines ignite inside the tube, creating a volcanic blast of heat that can warp the walls and destroy the infrastructure. To solve this, engineers designed a system where a high-pressure gas generator would eject the heavy missile into the air like a jack-in-the-box. Only after the weapon was clear of the ground would the main motors ignite. This meant a silo could be reused, and the weapon could be kept in a state of permanent, frozen readiness. The transition to solid-fuel motors meant that men like Petrov no longer had to wait for fueling trucks. The missile was always ready. But there was a paradox in this progress. As the weapons grew larger and their reach expanded to 10,000 miles, they became too heavy for the small, dirty conflicts that continued to break out across the globe. The missile had reached a point of over-evolution. It was so destructive that it could no longer be fired without ending the civilization it was meant to defend. The artillery had become a prisoner of its own power, buried in the dark, silent earth. While the superpowers were spending billions to bury their guns in concrete, the actual fighting was moving back into the brush and the mud. The massive, multi-stage rockets were perfect for a war that never happened, but they were useless against a truck-mounted machine gun or a hidden mortar in a jungle. The god of war had become a giant sleeping in a cave. But to understand how the guns survived the middle of the 20th century, we must look back to the winter of 1944, where the scale of the battlefield shrank down to the size of a single man's shoulder. By that final year of the war, the moving target had reached its most intimidating form in the heavy tank. For the infantryman, the traditional anti-tank rifle had become little more than a heavy metal stick, incapable of denting the thick steel plates of a German Tiger. The race between armor and velocity had reached a human breaking point. Corporal Miller was one of the men who stood at this crossroads. He was not behind a concrete wall or a 3-ton shield. He was in a shallow hole, bracing a hollow metal tube against his shoulder. This was the bazooka. Miller was holding the power of a heavy artillery battery in a 3-foot pipe. As the Tiger approached, the vibration of its engine rattled the fillings in his teeth. He had to wait until the steel was close enough that he could see the individual links of the tracks. The bazooka did not rely on the speed of the projectile to punch through armor. Instead, it used a shaped charge warhead, a chemical solution to a kinetic problem. When the rocket hit, it created a focused jet of molten energy that could burn through inches of hardened steel. Miller held his breath, squeezed the trigger, and watched the rocket bridge the gap. In that second, the individual soldier became a lethal participant in the artillery duel. The gun had become portable, while the infantry was finding ways to carry their own fire. The big guns of the later Cold War were facing a new, invisible enemy. By the later decades of the century, the artillery could no longer rely on distance or camouflage for protection. Technology had reached a point where a radar beam could track an incoming shell and pinpoint the location of the gun before the shell had even reached the top of its arc. Any gun that stayed in one place for more than a few minutes was effectively a target for immediate destruction. This reality gave birth to a weapon that looked like a monstrous, 8-wheeled armored truck. Driver Kowalski was at the wheel of this evolution. His job was the shoot-and-scoot maneuver. Every time a heavy howitzer fires, it kicks up a massive cloud of dust that acts as a beacon for counter-battery fire. The vehicle would roll into a clearing, the hydraulic jacks would snap down to stabilize the frame, and the turret would unleash a volley of 6-inch shells. But the moment the final round left the barrel, the clock started ticking. Kowalski did not wait to see where the shells landed. He would slam the gear lever into place and initiate a displacement while the smoke was still clearing from the muzzle. The gun had found its wheels. Before the enemy's counter-battery radar could even process the data and relay it to their own batteries, Kowalski's truck was already a mile away. He kept the vehicle hidden behind a different ridge or tucked into the shadows of a new tree line. The design of the Dana was a rejection of the old rule that a big gun had to move on heavy metal tracks. While most armies still insisted on mounting their howitzers on tank hulls, these designers realized that wheels offered a level of speed that tracks could never match on a road network. The vehicle could travel at 80 kilometers per hour, allowing it to vanish and reappear across an entire sector while tracked units were still struggling with their logistics. This was a vital victory for the survival of the artillery. The gun did not survive by getting bigger or more armored, but by becoming a ghost that haunted the battlefield. The artillery had transitioned from a static line of iron into a fluid, vanishing force. It was no longer about holding a position. It was about the ability to strike with overwhelming violence and vanish before the world could hit back. The gun had finally learned how to run. But by the late 1970s, survival depended on something more than just wheels and engines. The gun needed a brain. The targets on the battlefield had become so fast, specifically the low-flying strike jets and agile armored columns, that the human nervous system was becoming a bottleneck. To understand how the artillery stayed relevant, we must look at the moment the machine took over the act of hunting. This shift was vividly illustrated during the border skirmishes in 1982. Technician Reed was part of a unit operating a weapon called the Valkyr. On the surface, the Valkyr did not look like a piece of high-tech artillery. It looked like a standard 4x4 supply truck with a simple canvas canopy. This was a deliberate deception. In a world of satellite reconnaissance and high-speed aerial photography, a visible missile battery was a dead battery. Reed waited for the order to shed the disguise. When that order came, the truck would stop and the canopy would fall away to reveal a hidden rack of rockets. But the secret was not just the rockets. It was the warhead. Reed spent his time carefully inspecting the epoxy resin lining of these projectiles. Embedded within that resin were 8,500 precision-tooled steel balls. When the rocket detonated over a target area, it did not just explode. It created a lethal, invisible cloud of metal covering 1,500 square meters. The Valkyr was a bridge between the old world and the new. It used a relatively simple truck and a basic rocket, but it married them to a decentralized radar system that calculated exactly when and where to unleash that cloud of steel. Technician Reed knew that his weapon could turn a forest into a graveyard without ever needing to see the enemy. The gun had become an invisible ambush. But the most profound change was happening in the sky. For decades, anti-aircraft gunners had relied on manual tracking, literally pushing the gun with their feet or cranking wheels to follow a target. This was an era where weapons like the Duster anti-aircraft vehicle failed because human reaction time could not keep pace with a jet moving at 600 miles per hour. 3,700 of those vehicles were built, and almost all of them were rendered useless by the sheer speed of modern flight. This is where Operator Chen enters the story, sitting inside the turret of a Gepard. The environment inside the Gepard was a radical departure from the muddy gun pits of the past. It was a sterile, air-conditioned space filled with green radar sweeps and digital displays. Operator Chen did not look through a glass sight. He watched a computer-calculated indicator on a screen. The turret moved with a high-pitched whine from the tracking motors. Chen was not aiming the twin 35mm cannons himself. The computer was doing the work. The system was integrated with a search radar that could find a target 15 kilometers away and a tracking radar that could lock onto it with total precision. The machine was hunting. The algorithm would calculate the wind, the air temperature, and even the wear on the gun barrels in real time. Chen's role was reduced to a single decisive act of monitoring the system's health and pressing the firing stud when the computer confirmed a kill solution. This was the closing of the window of survival for the enemy. In the old wars, an aircraft had a good chance of surviving a pass because the gunners had to guess the lead. With systems like the Gepard, the computer solved the geometry of the intercept in a fraction of a second. The machine had effectively removed human error from the equation. Pilots stopped flying high to avoid the big missiles. But when they flew low, they ran directly into the digital brain of Chen's cannons. The machine had finally outpaced the eye. Technician Reed's rockets and Operator Chen's automated turrets represented the same fundamental evolution. The gun had become a computer peripheral. The survival of the artilleryman no longer rested on his physical endurance or his ability to lift heavy shells in the mud. It rested on his ability to maintain the sensors and trust the software. By the end of the 1980s, the battlefield was no longer a contest of maneuver between men. It was a contest of systemic readiness. The god of war had traded its iron soul for a digital one. The era of the mass barrage was being replaced by the era of the precision-timed, high-intensity strike. A single vehicle could now do more damage in 10 seconds than a whole regiment could do in an hour during the 1940s. The gun had survived by becoming a specialized, automated shield. It could now react to threats the human eye could not even see. Now we return to that frozen foxhole in 1944. The German wave had crashed into the position held by Private Outlaw, but when the thumping finally stopped, he did not find a battlefield. He found a void. The horizon he had been staring at for days was simply gone. The trees, the stone walls, and the very shape of the ridges had been ground into a fine grey powder. This was the torn whole, the physical manifestation of 20th century industrial output concentrated onto a single map coordinate. For Outlaw, The survival of the gun was not a technical question. It was a terrifying, absolute fact of nature. To understand how that erasure became a digital certainty, we must look to 1991. Sergeant Hakes did not live in a dirt-filled pit or a camouflaged trench. He lived in the air-conditioned cab of a multiple-launch rocket system parked in the middle of the Iraqi desert. He was not wrestling with hand wheels or estimating wind with a wet finger. He was watching a digital map screen that did the work that once required 1,000 men and a forest of paper charts. Consider the distance between the foxhole of 1944 and the cab of 1991. In the Second World War, a barrage was a chaotic, rhythmic pulse of individual shells. In the desert of the Middle East, Hakes pushed a single button and unleashed a saturation strike that the enemy would come to call steel rain. 2 pods fired 12 rockets in less than a minute. Each of those rockets carried 644 submunitions, small bomblets that saturated a square kilometer with the destructive power of a full artillery battalion. Hakes stepped out of his high-tech cab and looked across the dunes at the silent, empty horizon. Later, he would visit a museum and find himself leaning against a rusted French 75 from a century before. Hakes reached out and touched the cold, unmoving steel of the old carriage. He realized that the answer to how the gun survived was not found in the silicon of his computer or the speed of his rockets. It was found in the relentless human drive to project power across the distance. The gun survived because it stopped being a simple machine and became a system of survival. His hand remained on the old barrel, a bridge between the grease of 1897 and the silicon of the modern age. The god of war had found its final, perfect form. The destruction Private Outlaw witnessed in the snow of Europe was eventually scaled into a system of total erasure. By the end of the century, the gun had survived the arrival of the jet and the main battle tank by becoming a digital architect of the landscape. It no longer simply fired at a visible target, it edited the map itself. Years after the fires of the Persian Gulf were extinguished, Sergeant Hakes stood in the quiet of a museum. He stopped before a rusted French 75, the same design that had triggered the quick-firing revolution in 1897. Hakes reached out and placed his palm against the cold, unmoving steel of the carriage. He could feel the grit and the faint scent of old grease still clinging to a machine that was nearly a century old. An older veteran stood nearby, a man who remembered the back-breaking labor of the manual breech and the suffocating smell of cordite in a muddy trench. In that moment, the answer to the question of how the gun survived when the world outran it became clear. The answer was not found in the silicon chips of a computer or the horsepower of a modern engine. It was found in the relentless human drive to project power across the distance. The gun survived because it stopped being a simple machine and became a system of survival. It evolved from a heavy iron tube into a ghost, then into a silent sentry in a concrete silo, and finally into a digital pulse. The technology changed, but the intent remained identical. Whether it was a crew in 1916 timing their rhythm to the heartbeat of a howitzer, or Sergeant Hakes monitoring a satellite link in the desert, the goal was always the same. A soldier must reach out and touch the enemy before the enemy can reach them. The gun did not just keep pace with the world, it defined the boundaries of where a man could safely stand. This is the part of the story that most accounts skip. We focus on the caliber, the range, and the armor-piercing statistics. But we forget that the gun is the most persistent tool of the modern era. It is the bridge between the industrial grit of the 19th century and the digital precision of the 21st. It survived because we refused to let go of the ability to control the horizon. We see the zenith of this evolution today in the face of a young cadet looking through a modern digital sight. He does not have to worry about the physical weight of the shell or the violent recoil of the carriage. Those problems were solved by men who died long before he was born. But as he adjusts his focus, his eye reflects the same ancient, steady concentration of every gunner who came before him. He is the latest link in a chain that began the moment a human realized they could win a fight from a mile away. The gun had finally become the system. As we look at the modern battlefield, where autonomous drones and high-speed missiles dominate the headlines, the towed howitzer and the rocket pod remain. They are there because they are reliable, persistent, and offer a level of immediate, crushing power that no other technology can match. The god of war did not retire. It simply moved into the software. The era of the gun has not ended. It has become the very air we breathe in the world of modern conflict. From the mud of the Western Front to the sands of the Middle East, the story of the 20th century was written in the language of the barrage. It is a language of distance, of precision, and of the enduring human will to master the reach of the strike. If your father or grandfather served in an artillery battery, a rocket crew, or as a forward observer, I would be honored to read his story in the comments below. Please tell us about his unit, the caliber of the guns he served, and the specific memories he carried home from those years. Those personal details are the actual record of the God of War, and they deserve to be preserved by those who remember them. Thank you for watching, and I look forward to sharing more of these stories with you soon.